Everyone, now we will discuss rat swarm optimizer. This is a novel algorithm that we can use to solve different global optimization problems. This algorithm is basically inspired by the rat's behavior in nature. Here you can see the list of topics that we will cover in this video. First, we will discuss what is this algorithm all about, algorithm inspiration, how this algorithm works, different mathematical models used to design this algorithm. Then step by step we will discuss how this algorithm is working. And last we have algorithm advantages, disadvantages and applications. So we can apply this algorithm to a variety of optimization problems like to optimize engineering designs in routing, scheduling, machine learning. Like that we have a number of applications because this algorithm is compared with 8 different well-known optimization algorithms and it is also applied on 6 different real-life constrained engineering design problems, and this algorithm results are highly effective as comparison with other algorithms, so we can use this algorithm to solve a variety of optimization problems. So first we will discuss what is this algorithm all about and how it is working. Algorithm inspiration. So this algorithm is introduced in year 2020. So in this algorithm, rats collective behavior and their aggressive behaviors are modeled. So rat swarm optimizer is inspired by the chasing and the fighting behavior of rats in real life. And this algorithm specially highlight their aggressive and social skills during hunting prey. So as this algorithm is inspired by the rat's behavior, so first we will discuss rats behavior, how they chase, fight and hunt. After that we will discuss how this algorithm is working, means how the rats behaviors are modeled in this algorithm to find out the solutions of different optimization problems. First we will discuss their social intelligence. Rats display a highly social behavior. They work in groups, share information, and support one another in achieving goals. So you can see here in real life, rats live in groups, and in their groups, they have both males and female, and they also share information with each other and they also support one another. So in this algorithm, we will consider each individual rat as the problem solution. So as that live in group, they share information, support one another. So in this algorithm, the social aspects of rats' behavior influence how the solutions communicate and influence one another during optimization process. So each individual rat here represents a solution. So this is a swarm intelligence technique that is inspired by the two key behavior of rats in nature. First, chasing, second, fighting for prey. So these two behaviors are modeled in this algorithm. First we have chasing for the prey, chasing behavior. So first we will discuss their chasing behavior. You can see this is the mathematical equation used to model this behavior. Now we will discuss rats chasing behavior. So in nature, rats work together to chase prey and they match their moves and strategies in order to effectively corner or catch the target. So in this algorithm, this behavior is simulated as the exploration phase. So in Meta-heuristic algorithms, during exploration, all search agents will explore the solution space and they will search for the best solution. So same in real life, rats work together, they share information. So here in this algorithm, same behavior is simulated as the exploration phase. So in this algorithm, each rat represents a problem solution. So during exploration, rats searching through the solution space to find promising areas. Next behavior, we have the fighting behavior. Now once the target is cornered, now rats will fight aggressively to grab the food. So here rats display aggressive fighting behavior to secure the food, and in this algorithm this behavior is modeled as the exploitation phase. Done. So we have chasing behavior that is modeled as exploration phase of this algorithm. Then we have fighting behavior that is modeled as the exploitation phase of this algorithm. In chasing behavior in real life, as rats are searching or they are chasing the target, working together using different techniques to catch the target. Same in this algorithm, we will use different search agents. Here we have rats as the search agent, and each individual rat is our solution. Our search agents will explore the solution space to find out the best solution. Then we have the fighting behavior. Fighting behavior is modeled as exploitation phase. We will search around the good solution. So now we will discuss the mathematical models of this algorithm. Then step by step we will discuss how this algorithm is working. So we have rats population. Rat population means we have a set of candidate solutions for any problem. Next, in this algorithm, we have a fitness function. You can define here your objective function of the problem. So whatever problem you're trying to solve, accordingly you will declare here objective function. So each rat is a solution. We will evaluate each solution by using this objective function, and we will check the quality of solution. Done. So each rat is here a solution. So we will use our objective function to check the solution quality. Then we have different mathematical models for the chasing and fighting behavior. So in chasing behavior, rats chase prey by updating their position in the search space based on their own experience and the information shared by the other. So in chasing behavior, what we have to do, we have to move the search agents in the solution space. So we have virtual rat as the search agents. Now we have to move them in the search space so that they can find out the best solution. So we will update their position in the search space. Now how we will update their position? We will update their position based on their own experience and the information shared by other. Done. So as we already discussed, rats display highly social behavior and they work in groups, share information and support one another. The same behavior is modeled here. So in this mathematical model, we will update the position for each search agent by adjusting their position relative to the best search agent. That is the optimal solution found so far. So here you can see this represent the current position of our search agent. Then this is the best known position, that is the optimal solution. After that, A and C, we have the parameters that control the degree of exploration and exploitation. R and C, we have the random number that influence the randomness in the position update. Parameter A is responsible for exploration, and it also ensures that rat's new position is influenced by its current position and allowing algorithm to search new areas of the solution space, and it encourages the search agents to explore other potential solution. Then we have next parameter C. This is responsible for exploitation. Using this parameter, we are guiding the rat's movement toward the best known solution. So this term encourages the swarm to refine its search near the optimal solution and improving the accuracy over time. Then we have a range of values like for R and C. R, that is the random number between 1 and 5. It helps to maintain the diversity in position of search agents, and it also ensures that all the search agents will explore different part of the search space. Another random number C, range for this we have between 0 and 2, that is used to determine that how aggressively the rats move toward the best solution. Next model for the fighting behavior, the prey is the good solution. So in this algorithm, for the simplicity, we will consider the prey or the target as our good solution. So whatever best solution you have, we will consider it as our target. So once the target is found, then the rat becomes more aggressive in their movement. Now rats will become more aggressive in their movements. They will converge toward the best solution. So in real life, when the target is found, rats display a aggressive fighting behavior to secure the food. So it's same in this algorithm. Once a good solution is found, rats will become more aggressive. Rats means our search agents will become more aggressive in their movements, converging toward the best solution, because each search agent want to find out the best solution. So once the good solution is found, always start converging toward the best solution. So this is the exploitation phase of this algorithm, where algorithm refines its search near the optimal solution. Using this equation, we will update the position of rat in this algorithm. This represents the updated position of any rat I in the next iteration. And here you can see this is the position of best search agent done, means the current best solution for that iteration done. In each iteration, we will update the best search agent and we will compare new value with older value. So this is the current best solution. After that, we have the current position of highest threat in the search space. So here we have the absolute difference between the best solution and the current position. So this absolute difference is designed to direct the search agents to move closer to the best solution in a controlled manner. And the use of absolute value also ensure that position update is always positive and deriving the rats closer to the optimal solution and preventing any negative movement that might take them away from the promising area of the solution space. So this update rule ensures that every search agent in the swarm move toward the best known solution found so far, and over time this allows the swarm to converge to the optimal solution as the distance between all search agent and the best solution decreases. Then we have convergence. So as the algorithm progresses, the distance between current position and the best solution decreases. That leads faster convergence toward global optimum. So here we have chasing phase and the fighting phase. In chasing phase, rats will explore the solution space and they will chase the better solution by updating their position based on their individual knowledge and the collective swarm behavior. Second, we have fighting phase, where once the promising solution is found, let's converge toward this solution aggressively. So throughout this optimization process, rats will exchange information that leading to improved collective performance over time. Now step by step we will discuss how this algorithm is working. Again I'm repeating, this algorithm is modeled how rats aggressively chasing a target is the solution here, and they are working together updating their position based on their individual and shared information. They will update their position and try to find out the best solution, that is the optimal one. So in input we have the rat population, as output we need the optimal search agent that will display the position of best solution. So in the end we need the position of the best search agent, that is the optimal one, who will display us the best score, and we will check that solution fitness score, that is the optimal solution. So first step, we will initialize all the important parameters. Here you can see we have different parameters used in this algorithm. We have A, C and R. These parameters are used in mathematical models. You can see we have parameter A and C. They are used to perform exploration and exploitation. We can adjust the value of these parameters to perform exploration and exploitation phases. And here you can see R, that is the control parameter, value between 1 and 5, and C is the constant parameter, value we have between 0 to 2. And for parameter A, we will calculate the value using this equation. So we have R and C, the random values. For R, we have value between 1 and 5. For C, value is between 0 and 2. And here for A, we will calculate using this. So first we will initialize our parameters. Then we will initialize the population for the search agents. We will randomly initialize the position for each search agent in the search space. So using this equation, we can randomly initialize the position for each search agent. So here our search agent is rat. So for each rat, randomly initialize the position. So using this equation, we can initialize. So according to your objective function, we will define the upper bound, lower bound. Rand is here a random value that is normally distributed between 0 and 1. So using this equation, we can generate random position for each search agent. Next, we have to define the dimension. Suppose if you have two dimension, then the position value would be for first dimension, second dimension. Suppose if you have 30 dimension, then you have to calculate the position value for the search agent for each 30 dimension. So initialize the position. Next step, we will apply the objective function on the search agents and calculate their fitness score. Now we will calculate the fitness value for each search agent and we will check their performance. So using objective function, we can check the quality of solution. Done. The next step, we will save the best search agent. So if you are doing the minimization, we will consider the minimum value as the best value. Suppose we have total 10 search agents. For 10 search agents, we calculated the 10 fitness values. Now if we are doing the minimization, we will consider the minimum value among these 10 as the best value, and if you are doing the maximization, consider the maximum value among all as the best value. So in this step, save the best search agent. Now the main loop for this algorithm started here. This is the current iteration. So we repeat this loop until the stopping condition is met. If you initialize your total iterations, suppose 100, then the loop will repeat 100 times and after that it will display you the best solution. So in next step, for each search agent, we will update their position in the search space using this equation. Now you can see here we have this equation that we will use to update their position in the search space. So inside this equation, that's both behavior are designed. For example, you can see this is the equation that we can use to perform rats chasing behavior in this virtual environment. So how we will update the rats position? We will update the rats position based on their position with respect to the best search agent obtained so far. This is the rats position and this one is the best position, that is the optimal solution. This is our best search agent minus rats position. So now suppose for each search agent we updated their position. Now for each search agent we will check whether any search agent goes beyond the boundary or not, and if any search agent is not inside the boundary, then we will again calculate the position for that. After that we will calculate the fitness value for the updated solutions. So once the new fitness values are calculated, again we will update our best solution. Then we will compare our new best solution with the older one, and if the older one is better, we will keep this, and if we obtain any new fitness score that is better, then we will consider that as the new best score. Then increment the counter, repeat the loop until the stopping condition is met. And once the stopping condition is met, we will stop and display the best solution that you found so far. So algorithm advantages, we have strong exploration and exploitation phases. So we have effective balance between exploration means searching for new areas, exploitation means search around the promising solution. So by mimicking the chasing and the fighting behavior of rats, this algorithm maintain a good balance between exploration and exploitation phases that help the algorithm from getting stuck in local optima. Second, we have the simplicity of this algorithm. This algorithm is simple to implement and very easy to understand. You can see the structure of this algorithm. This is a very simple. We have few parameters. When we will compare the parameters with another algorithms, you can see we have just few parameters that we need to adjust. Then we have faster convergence. In this algorithm, we have the aggressive convergence during fighting phase that allow the algorithm to focus on high quality solution. So once it define the promising area, it leading to the faster convergence in some scenarios. Due to this swarm based nature, this algorithm can handle optimization problem with large number of dimension. Dimension means large number of design variables. After that, we have different disadvantages. So like other swarm intelligence algorithms, this algorithm can suffer from premature convergence, especially if the search agents converge quickly to a suboptimal region. So there is a risk of premature convergence, and this is more common in complex and multimodal functions. It depends on your parameter choice. If your parameter choice is poor, it can lead to suboptimal result, slow convergence. Application, we can use this algorithm for engineering design optimization, network optimization, scheduling problem, energy management. Like that, we have a number of application because this algorithm offers strong acceleration and exploitation balance. But for multimodal complex problem, there may be this little bit problem, but for that we can create either hybrid approach or we can combine other methods to solve that. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.